Magnetic fields 4. Electromagnetic induction. What does electromagnetic induction mean? Well, it basically means making something happen, inducing. What are we inducing? We're inducing an EMF using a magnetic field. Electromagnetic induction, making electricity using magnets. Now, when we move a magnet into a coil, it produces electricity. There's a coil, we're moving a magnet into a coil, and we induce an EMF. We make an EMF happen. An EMF is basically a voltage, so we are making a voltage happen. If we have a circuit, then we also get an induced current. We also induce a current. But even if you didn't have a circuit, you'd still get an EMF. To induce an EMF, you need a magnetic field, you need a conductor, and you need relative movement. In this case, the magnetic field is from the permanent magnet, the conductor is the coil, and the relative movement is me moving the magnet into the coil. The size of the EMF will depend on the strength of the field, the length of the conductor, for example, the number of turns on the coil, and the speed of the relative movement. Okay, here's another way of inducing an EMF. This time I'm just moving a wire. I've grabbed hold of the wire and I move it through a magnetic field. And it's the same thing again. A conductor is moving through a magnetic field and we are inducing an EMF across the ends of the conductor. If you do this, one end of the conductor will become positive and the other end will become negative. You don't need to be able to figure out which one. Now, Michael Faraday, I mentioned in an earlier video these flux lines in space. And Michael Faraday imagined that what the conductor was doing was cutting flux. It's cutting the flux lines as it moves through the field. And he reckoned that the size of the EMF is proportional to the rate of flux cutting, the amount of flux that you cut every second. And so we get Faraday's law. Faraday's law says that the induced EMF is proportional to d phi dt. The induced EMF is proportional to the rate of change of flux, or if you like, delta phi over delta t, or the rate of flux cutting. Faraday's law. Now, in SI units, very neatly, the induced EMF equals d phi dt. If we have a coil with n turns, then this idea of flux linkage, the EMF equals dn phi dt, the rate of change of flux linkage. And then lastly, we put a minus sign in there, and that's due to something called Lenz's Law, which I'll talk about very shortly. So the induced EMF equals minus d phi dt, or minus dn phi dt, if you're talking about a coil. Here's a question for you to have a go at. A wire of length 12 centimeters moves at right angles through a magnetic field of strength 25 millitesla at the velocity of 0.8 meters per second. Calculate the induced EMF across the ends of the wire. And the answer is that. And the way that we do it, how much flux is cut per second? So the flux cut per second, think about the area swept out by this wire, and then multiply that by B, and that will tell you psi, the flux cut per second, and that will equal the induced EMF 2.4 millivolts. So what is Lenz's law? Now, Lenz's law is this: the induced EMF will always try to oppose the flux change causing it. Imagine I'm pushing my magnet into the coil. What the EMF will do is it will try to stop me. It will say, go away, I don't want you coming in here. It doesn't want me to push the magnet in. But then if I pull the magnet out, the EMF will try and stop me. Please don't go away, stay in here. The EMF will basically always oppose what I am trying to do. Why does it do that? And it's basically conservation of energy. If I'm cutting flux, then basically I have to do work to cut flux. The energy has to come from somewhere. If you imagine instead of a meter there, if there was a light bulb and I'm moving this magnet in and out and the light bulb is flashing, where does the energy come from to flash the light bulb? And it's coming from me because I have to do work. And basically what the EMF is doing, it's a little bit like friction. Friction always opposes motion. Friction will always try to slow you down or stop you speeding up. And that's what the induced EMF does. Electromagnetic damping, if you like. And so Lenz's law says the EMF always tries to oppose the flux change causing it, and that's why we have the minus sign. You might have to explain Lenz's law, but in any kind of sum, I wouldn't worry too much about the minus sign. It really doesn't come into any calculations. Now, this may seem trivial, but you'd be amazed at how many students get motors and generators mixed up. The motor effect, you put in electricity, you get motion. The generator effect, you put in motion and you get electricity. It's the opposite thing. If you see a question, is it a motor, is it a generator? Now, an AC generator, these are on the syllabus. You do need to know about AC generators. We have a coil in a magnetic field. You turn the coil and you get an AC voltage out. Okay? You need slip rings. If you didn't have slip rings, then your connections would get tangled up very, very quickly. But with slip rings, you turn the coil and you get AC, alternating current, and AC voltage coming out of the coil. As the coil rotates in the field, the flux linkage, the amount of flux going through the coil, is changing continuously, and alternating EMF is induced across the ends of the coil. This is important. This is the first graph is flux linkage. That's the amount of flux going through the coil, and I've drawn it as a cosine. Flux linkage in the coil, and as it's a cosine, I can write n phi equals n phi naught cos omega t. Phi naught being the maximum. So the amount of flux at any time, n phi equals n phi naught cos omega t, where omega is the angular velocity, 2 pi f. If we differentiate that, we get dn phi dt equals minus n phi omega sine omega t. And so my induced EMF, which is minus dn phi dt, is going to be n phi omega sine omega t. And then the maximum EMF, a common question it asks you to work out, is the maximum EMF is going to be n phi omega. A very common question is, you're given the graph of flux linkage and you have to sketch a graph of the EMF, or vice versa. And the thing to note is that they are 90 degrees out of phase with each other. And if the flux linkage is a cosine, then the EMF will be a sine. Here's a question for you to do. I'll leave you to read it and then you can have a go at it. And the answer is that.